sort of the broader topics at the top in that diagram, and then sort of an explanation in paragraph form after it. I think the biggest take home for computational thinking is that you're already probably doing it. It's just making it more explicit. And the definition I've been using for it is computational thinking is like a means to a way of thinking about problem solving that's prepared to use a computer. I'm a firm believer that you do not need a computer to be doing computational thinking, but there are ways you can do other activities that lend themselves better to using a computer. So some of them being, like when you're collecting data, I'm not going to read all of them, I shouldn't have picked the first one, but so some of the data practices, you can be collecting data in a way that works really well with Excel, or using some sensor that works with computer software that if you had, instead of the 30 data points in the classroom, you had 30 million data points. Those sorts of things to keep in your mind is really where we see computational thinking. Sometimes that's a little bit hard to wrap your mind around. A couple of my take-homes are usually, like if you're collecting data, you should have, like, don't merge any cells. If you've merged cells, then something has gone wrong and the computer's not going to be able to understand it. If you're collecting data that are words, okay, I guess I could use this second sheet where I tried to pick out a STEM activity that's a good STEM activity without computational thinking, and then what it might look like with computational thinking. I realized I was about to use the first example. So if you're, I used to do mystery minerals. So, give a bunch of minerals and you do the tests and you collect the data. And what I realized at one point was we have like you could collect a lot of great quantitative data, but then some of the qualitative data, so like, oh, it looks yellow, or someone would put, it looks orangish. I'm thinking of sulfur. I don't know why you get orangish sulfur, but go with me. I'm a biologist. I don't know why I chose a geology example. But while those two colors may be super similar, a computer doesn't know that. A computer knows what those words are. Even further, I like to use Google Forms a lot in my classroom because I can control what you can answer. So I don't do any short answer if I want to sort by it. So I may give options of colors. I'm only aware of, the 8 colors that comes in the 8 box of crayons, and then you could throw a light or a dark on there. A computer can understand what those words are, that they're the same, but it might throw it off if you capitalize something. Kids really like to spell words wrong in new and exciting ways. That'll mess up a computer. So keeping in mind those things is a computational thinking bit. And you may never touch a computer when you're doing that activity, but having that built in is a great computational thinking practice, especially the conversations around those. So, by the way, I had a lot of coffee, so I'm shaking. Just go with it. I'm weak from not being in a classroom. I can't handle the coffee the same way. So modeling and simulation practices. So this might be something that you would immediately jump to, like, oh yeah, computational thinking. You got my favorite is when you go to the planetarium, especially. I practically grew up at a planetarium. I'm actually from Geneva. I don't harbor any Batavia, Geneva things. But they had the great, you put in the planets and set them running, and it would show you what would happen. I could never get a binary star system working, but you think those sorts of simulations. But you really don't have to create those to be doing computational thinking. So one thing that we're going to do in one of these activities, I do not remember the actual names, I have my weird names for them, but one of them is designing a simulation without actually making it. Just the thought processes of designing what you would do is enough. Because then, hopefully they have a computer science class at some point if they're interested in it, but thinking through how you would make that is the important part in a STEM classroom. If you are, just a quick show of hands, does anyone do any coding or anything like that? Okay. I don't want to assume you don't. Actually, a quick show of hands, 5 being really comfortable with computational thinking and 1 being super not comfortable with it. Where is everyone? Cool. Okay. That gives me space, like it gives us a good groundwork, but it gives me space to improve. Another fun one I like is assessing computational models, where you put kids in the place of like, oh, this is wrong because, you know, this isn't what happened when we did our experiment. I added more yeast and, you know, it rose now, which is funny. I baked bread and I don't remember it proofed more. But in this model, it shows that it's not doing that. You know, a little assessing of them is a great skill. And so a lot of these don't require coding at all. As I say that, we move on to computational problem solving practices that has programming right in there. But such a small part of programming is coding. And what I mean by that is, so I'm a terrible coder. I'm going to graduate with a computer science master's degree this year. I'm an awful coder. I mean, most middle schoolers that have been doing it for 2 years are better than I am. I'm not saying all middle schoolers do, but the ones that have are better than I am. But coding is like 20% of programming. The rest is planning it out, figuring out your algorithms. In one of the, I think it's Feeding the World activities where you do the Punnett squares. We did algorithms on paper for a step-by-step process on how to do every Punnett square. And if you guys seen the dad that tells his kids to write down how to make a peanut butter and jelly sandwich, and the dad's like a real jerk, it's great. So computers are really dumb. They'll do exactly what you tell them to do. Like my 3-year-old, I tell him to go to sleep and he just goes like this. Like, that's not what I meant, obviously. So what we did is we did the same thing. We had them write out exactly what to do, and every little bit of lack of specificity. So if you have 7 steps to do it, really you probably need like 28. The best descriptions, the best, you know, writing out your own experimental design is going to be generally more steps. I think that's my 3rd example here. Yeah. Using a colloquial, I don't know why I chose that word. Using like an idiom, a computer doesn't know what you mean when you tell it. It will do exactly what you say, literally. And so if you want to make something more computational thinking-y, be really strict about, you know, what do you mean by this? You said put this in that. Does that mean like the jar? Does that mean just pour it in? Does that mean the more specific you can be, the better. Really granular steps. You know, measure this out into this, and then bring it back to your lab station. That's a bit much. But a lot of steps. It's how a computer works. It's these super basic bits. So I said 25% is, what did I say? 20% was coding. More than half of the time is troubleshooting and debugging. And when you think of debugging, you know, the story of debugging comes from back when it was literally wires everywhere, and a moth kept flying onto, like, shorting the wires, and so that was why they call it debugging. Trying something, especially in engineering design, finding the component that went wrong and why it went wrong and how it went wrong is the same set of skills and the same thinking as debugging a program. It's just probably a little bit more fun. I have spent more time than I would care to admit essentially doing nothing, trying to debug something. Also, decomposing problems into very small components and manageable ones, and then going through that. The more decomposition you can do, again, it's the same skill. When you look at a program to do something big, like solve a puzzle, there are a lot of little components that you have to separate out and make on their own. Finally, system thinking. There's a lot of interacting components every time you're making a program, every time you're working with a computer. Thinking about how relationships within systems work. The example I give is a water cycle activity. Being able to abstract, so you could look at your local water cycle, but then thinking about a water cycle like in the desert and picking out what components are the same, like the part of the water cycle where water goes from the atmosphere to the ground, and identifying something similar there is another really important skill of, we call it abstracting. I think that's what I wanted to cover for now. Are there any questions just right off the bat that I can answer? I'm trying to be careful about. Okay. So no questions right away. Anything you're hoping to get out of this? Because I might be able to, I guess, answer that sort of thing. What are expectations for the computational thinking bit? Hopefully having something to come away with, maybe a definition. Being able to, write down that you have those hours and tell your principal that you're doing computational thinking. I was in a classroom. Well, I don't want to just keep talking for talking's sake. So,
fine.
yeah.
We are ready to move.
Okay,
on.
great.
We're ready. We can use that.
I'll be interjecting throughout. There are a couple of spots in the lesson plans. For example, in the objectives, I kind of starred the more computational thinking objectives, and I added the practices at the bottom. And those practices relate to these. It's just an abbreviation of what type of practice it is, and then the number in the column.
Okay. Okay, so just so that all of you know, we are streaming this at the same time. So